Let's talk a little bit about the relationship between pKa and resonance. If we look at these particular substituents here, we've got a phenol with a bromo substituent on the pair position, and we've got another phenol with a methoxy down here. The pKa of this one is lower than this one by almost a full point. Okay, so lower pKa means that this guy is more acidic than is this one. Whenever you're looking at the acidity of a particular compound, what you really need to do is you need to take the hydrogen off and look at what's left. So really what we're looking at is the stability of the conjugate base of this particular acid. And the acidic portion of this is obviously this hydrogen that's attached to the oxygen there. So here we go. I want to look at these two and then we'll predict this in just a minute. So this is 9.17 and here we've got 10.20. Okay. Well, this guy is inductively pulling electrons out. Okay, everything's good. The difference between him and this one is that this oxygen is pretty willing to undergo that resonance shift, just like what we were talking about in lesson 9. So in other words, electrons can go into the ring and put negative charges throughout that ring. Negative charge being pushed in the ring doesn't exactly help a negative charge on this side be stable. Bromine, being a deactivating compound, is not as willing to put electrons in there. He's inductively even pulling electrons from the other side, and that's what makes this guy more acidic than this one. Now, let's compare the opposite type of scenario. What happens when you have an acid like this? We know it's acidic because we've got a positive charge up here on the nitrogen, so a hydrogen's ready to come off pretty easily. But notice that this guy is way lower than this one right here. Okay, well again, in this particular case, we've got electrons that are willing to go into the ring, but why is that a problem? Well, to really look at the acidity there, we've got to remove a proton and look at the conjugate base. So once we take off a bromine, then we're going to look at what we've got at that point in time. Now we already know that the pKa of this one is 3.86 and of this guy it's 5.29. Well, the reason for that is because, again, bromine is pulling electrons to this side, right? And NH2, being a strong activator, one of its resonance structures is to actually have a negative charge at the pair position. So that kind of works for bromine. He's pretty happy with that, right? On the contrary, and the reason why there's such a huge discrepancy here, once you have the NH2, that's also trying to, or willing to, shall we say, donate its electrons into the ring, as is the oxygen that's on the other side. So they're kind of fighting over who's going to end up putting the electrons in the middle. So it's almost like bromine kind of helps a little bit more so than this guy does. Another way to look at that, if we go back to this structure, is that bromine is not as stabilizing of this acid as oxygen is. Oxygen is more stabilizing of that positive charge because it's willing to put electrons into the ring. That's another way to look at it. Okay. So now if we look at a nitro group, what do we think is going to actually be the case here? If we look at a nitro groups are incredibly deactivating. They pull electrons out of the ring. So that's going to leave positive charges behind here, which shouldn't be a surprise that the pKa of this one is 7.14, because a positive charge helps negate or acts out, neutralize that negative charge from up here. And down here, the pKa of this guy is very, very low, because he's going to help the conjugate base to be rather stabilized, but more so the NO2 is putting positive charges into the ring, and we don't need another positive charge hanging out there. Okay, so the removal of that will help that NO2 be stabilized. It's kind of a backwards way of thinking, and you have to remember when to go backwards and when to go forwards. But just try to think your way through a particular thing and say, okay, what is it that's going to help stabilize something? What is it that's going to hinder the stability of something? Thank you.